Okay, welcome to part 2 of the lecture on gases. I am trying to break it up a little bit because I don't want the files to get too large. But as I said in the previous, towards the end of that part 1 lecture, we were going to combine all these laws to the ideal gas law. Okay, let's look at all the laws that we've talked about so far. Boyle's law, where C is a constant, is expressed as V divided or is equal to a constant C over pressure. Okay, so C over P. And we know that this is a constant number of moles and constant temperature. That's the conditions for Boyle's law. Charles's law, we know that it's equal to, so volume is equal to a constant multiplied by the temperature. And we know that the number of moles it doesn't change, nor does the pressure. Those are the conditions for Charles's law. For Avogadro's law, we know that the volume is directly proportional to the number of particles or number of moles of a gas. So V is equal to a constant C multiplied by the number of moles of a gas. This is true if the pressure and temperature are constant. They're not changing. Okay? So we come over here. We can combine because the V is equal in all these cases. We then combine all these into one big expression. We can say V is equal to C1 over P multiplied by C2 over T multiplied by C3 times N. Oh, I'm sorry, I said over T. Let me say it again. V is equal to C1 over P multiplied by, this is Boyle's law, this is Charles's law, so multiplied by C2 times T multiplied by Avogadro's law, C3 times N. I have 1, 2, 3 here because my constants are different. They're constants, so it's a C, but they're different. And so I can combine all the constants together down here, C1 times C2 times C3, so I factor them out. And what I have left is T for temperature multiplied by N divided by the pressure. So all these constants, I can combine them into one super constant, right? And that turns out to be R. So R is equal to C1 multiplied by C2 multiplied by C3. And if I take R and I plug it in up here, I get V is equal to R times T times N over P. Okay? And the ideal gas law gets this form, which is the most familiar form. So if I multiply these two here to get rid of the P in the denominator, I get PV P times V equals N times R times T. This is the ideal gas law. This is another law that you need to know by heart. Okay. You don't need to remember how to derive this. I'm just showing you where it came from. Okay? But you will need to remember this law. Okay. If I look at an ideal gas, obviously that's what I'm looking at, we can calculate the value for R, the constant. How do I do that? Well, if I take PV equals nRT and I isolate R, I get P times V over N times T. Okay? For standard conditions, right, STP, what did we say? STP is standard temperature and pressure for 1 mole, right? So 1 mole of gas at 273.1 Kelvin and 1 atmosphere, we said, has a volume of 22.414 liters. So if I plug in all of these numbers up here, I get a constant of 0.08206 liter atmosphere per Kelvin mole. Okay? That is the ideal gas constant. The value is 0.08206 liter atmosphere per Kelvin mole. I will be providing this for you, so you don't have to necessarily memorize it, but you need to memorize that formula. Okay, let's look at some problems. Once again, I'm going to blacken this out so that we can work on the board, but I'm going to read them from the computer. Okay, calculate the ideal gas constant if the pressure is measured in torr instead of atmosphere. Okay, what do I know? That R, the ideal gas constant, is equal to PV over P times V over N times T. Okay, that's what I know. Okay, so instead of using the pressure in atmosphere, I need to use the pressure in torr because it asks me calculated what is the ideal gas constant if the pressure is measured in torr. And I know that 1 atmosphere, because this is standard, right? This is standard temperature and pressure conditions. My standard pressure is 1 atmosphere. How many torrs in 1 atmosphere? 760. So my pressure is not going to be, I'm not going to express it in atmosphere. It's going to be 760 torr multiplied by the volume, which is 22.414 liters. We said that's the molar volume. N is equal to 1 mole. And the temperature is 273.15 Kelvin. Okay? And if you do the calculations for this, you get 62.36 torr times liters over Kelvin times mole. Kelvin mole. Okay? That's the value of R if the pressure is in torr instead of atmosphere. Okay? Now let's look at the next problem. I'm kind of zooming by a little bit because you can always pause me and rewind me when you're doing this at home. The volume of an oxygen cylinder is 2.025 liters. So that's my volume, 2.025 liters. At a temperature of 32 degrees Celsius, so there's my temperature, the cylinder has a pressure of 945 torr. How many moles of oxygen gas are in the cylinder? What is its mass? What is its density? Okay, so I have 3 different things that I need to solve for. The number of moles of oxygen, the mass in grams of oxygen, and the density of oxygen. Okay. So, I can, first of all, get my temperature changed to Kelvin. So I add 325 Kelvin, or 273 Kelvin to get 305 Kelvin. Okay, that's my temperature. Now, you can do this. We know R, we just calculated. R is equal to 62.36 liters times torr over Kelvin times mole. Okay, that is the value for R in torr because we have the pressure given in torr. Okay, let's calculate N first because I know that volume, temperature, and pressure, and R, I know that it's a constant, but these 3 values are related to the number of moles through the ideal gas law. So I can write P times V equals N times R times T. To isolate N, I divide both sides by RT. RT cancels out, and I have N left on that side. Okay, so N is equal to pressure, which is 945 torr, times the volume, which is 2.025 liters, over my R, which is 62.35 liters torr over Kelvin mole. And then the temperature is 305 Kelvin. Okay, my torr will cancel out, my liters will cancel out, my Kelvin will cancel out, the mole is at the bottom, so it will come, because I'm dividing by a fraction, the mole will come on top. So N is equal to, if I do all that math correctly, N is equal to 0.1006 moles of O2. One hint is that the number of moles in general, when we're dealing with gases, is going to be a very small number, okay? So N is equal to that. I found N, I need to find the mass in grams. Well, I have moles. How do I go from moles to grams? We just did a ton of stoichiometry problems. The way to do that, we've done that before, is we use the molar mass to convert from one to the other. I have moles of oxygen. I need grams of oxygen. I know that the molar mass of oxygen, because I have 2 oxygens, is 32. So I know that 1 mole of oxygen weighs 32 grams. So this will give me the mass. The mass is equal to 3.218 grams of oxygen. Okay, now that I have the grams of oxygen, I have the mass, right? I have the mass in grams. I have a volume. I can calculate the density because I know density is given. Density is mass divided by volume. If I want to write this in grams per milliliter, I would need to convert the volume to milliliters, which would be equal to 2,025 milliliters. Okay, now I have both. I have the mass and the volume, so I can calculate my density. My mass is equal to 3.218 grams divided by 2,025 milliliters, and this gives me 1.59 times 10 to the minus 3 grams per milliliter for the density. Now, stop and ask yourself, does this make sense? Yes, it does, because I'm talking about a gas. The gas is they expand, so they take up a lot of volume, but they don't have a lot of mass per unit volume. So the density is going to be very small. The density of gases is pretty small. Density of solids, pretty high, because the molecules are really close together, whereas the molecules of a gas are very far apart. And so you don't have a whole lot of particles for the same unit volume as you would for a solid. All right, let's keep going. Dalton's law of partial pressures. Okay, I know there's a lot of laws, but you're going to have to be familiar with every one of them because we will use it. Dalton's law of partial pressure states that if I have gases that are in a mixture, so if I have several different gases combined in the same vessel, in the same container, they behave independently of each other and they exert the same pressure as they would if they were just by themselves. Okay? So if I have, let's say, a mixture of air in a container, and we know that air is made up of nitrogen and oxygen and a little bit of hydrogen gas and a little bit of water vapor, etc., and a little bit of argon. So all of those gases, they behave independently of each other, and they exert the same pressure that they would if we just had oxygen by itself in that same vessel, or we had water vapor by itself, or nitrogen by itself. So they do not affect the pressure of each other. That's what that means, that they behave independently. Then the total pressure of the system is given, of the mixture, is given as the sum of the individual pressures of each gas. So if this A was my oxygen, this would be the pressure of oxygen plus the pressure of B, nitrogen, plus the pressure of water vapor, etc., etc., however many gases you have in the mixture. Okay, so that's the law of partial pressures, or Dalton's law of partial pressures. Okay, let's work this problem on the partial pressures. I will once again read it, and then you will have it in front of you, hopefully, so you don't need to see it. Given a 2.5 liter container at 45 degrees Celsius, what would be the total pressure in the container from a mixture of 2.1 moles of sulfur dioxide and 1.8 moles of hydrogen sulfide? Okay, what do I have? I know the volume, so my volume is 2.5 liters. I know the temperature, which is 45 degrees Celsius. I might as well go ahead and convert it to Kelvin, because I will need to do that anyway. So plus 273, it gives me 318 Kelvin. Then I'm given the amount of moles of each gas. So I have, and instead of Na, I should do SO2. So I have the moles of SO2, which is 2.1 moles. And then the moles of hydrogen sulfide, which are equal to 1.8 moles. Okay, I'm asked to find the total pressure. What is the pressure of the system? Now, you can do this two different ways. Remember, we said that R is equal to 0.08206 liter times atmosphere divided by Kelvin times mole. Okay, so that is my R, my constant, ideal gas constant. Okay, I can figure this out two ways. I can use the ideal gas law to calculate the pressure that the first gas exerts. Then I can use the same ideal gas law to calculate the pressure that the second gas exerts, and then add the total. Or I could do it this way. I could add the number of moles of the two gases. So if I know the total number of moles, I can directly find the total number, or the total pressure, by using the ideal gas law once. I will show you both so that you know, you can prove it to yourself, that it doesn't matter which way you choose, you will get the same answer. Let's first do it by adding the total number of moles. So if I add these two together, I get, let's see here, 3.9 moles total of gas in my container. Okay, so to find the pressure then, I can use PV equals nRT. Isolate the pressure, I divide both sides by V. My V cancels. Okay, so I have nRT over V My N is the total number of moles, 3.9 moles. R is this value, times 0.08206, times the temperature, which is 318, divided by the volume, which is 2.5 liters, and I get a value of 40.71 atmospheres. That's my pressure, my total pressure. Now let's calculate this with calculating the pressure of each individual gas and then adding them together. So for that one, I'll use PV equals nRT twice for each gas. Okay, I will work it over here. You have these values, so I'm going to erase these so I have room. Okay, let's do the pressure for the SO2 gas. So P of SO2 times V is equal nRT, right? Divide both sides by V, cancel. So pressure of SO2 is equal to N times R times T over V. Okay, but the N is not the total number anymore. It's going to be 2.1 moles, which is the number of moles of just SO2 gas. So 2.1 mole times 0.08206 times the temperature. Everything else is the same. The volume is the same and the temperature is the same. So 318 Kelvin divided by the volume, which is 2.5. And the pressure of SO2 comes out to be 21.92 atmosphere. Now I can calculate the pressure of H2S the same way. I'm not going to isolate it again because it's the same thing. I'm just going to write it. So the pressure of H2S is going to be nRT, so N of H2S, RT over V. Okay, if I plug all of those values, so N is 1.8 now, 1.8 times 0.08206 times 318 over 2.5. That gives me a pressure of 18.79 atmosphere. Okay, now I have the two atmospheres, the two pressures of the gas. I can figure out the total pressure by adding. So we said total pressure is the pressure of the first gas by Dalton's law of partial pressures. The first gas plus the second, etc., etc. So pressure of SO2 plus pressure of H2S is equal to, so if I do 21.92 plus 18.79, you get 40.71 atmosphere, which is the same as what I got up here. Okay? So you can choose to do it both ways. All right, the last part then of the chapter on the gases relates gases to chemical reactions. So we've talked about chemical reactions in which we have one of the products or one of the reactants is a gas. We can take the stoichiometry part that we learned in chapter 7 and we can combine it with the gas laws that we just are learning in chapter 8, and we can solve stoichiometry problems. So here's a couple of these problems that I'm going to work out and show you how you can do that. Once again, I'm going to go back to a blank screen. I'm going to read this. All right. How many grams of calcium carbonate is formed if 3.45 liters of carbon dioxide measured at 45 degrees Celsius and 1.37 atmosphere react with excess calcium oxide? So here's my reaction. I have calcium oxide, solid, plus CO2 gas gives me calcium carbonate, solid. Okay, what is the first step? Make sure that the reaction is balanced. I have one calcium, one carbon, 3 oxygens, 2 plus 1 gives me 3 oxygens, so this is already balanced. Okay, I am asked to find how many grams of calcium carbonate is formed if I have 3.45 liters of carbon dioxide measured at 45 degrees Celsius and 1.37 atmosphere. Okay, we know how to use, or we should by now, from chapter 7, we know how to do stoichiometry problems where we go from grams to moles to moles to grams, right? So I'm asked to find the grams of calcium carbonate from CO2. I don't have the amount of CO2 in neither moles nor grams. But what I do know is that it's a gas, and it has the problem has given me the temperature and the pressure of this gas. So I can go to PV equals nRT, to the ideal gas law, and I can say, well, I have the pressure, I have the volume, I have the temperature, I know what R is because it's a constant. I can calculate the number of moles. And once I know the number of moles of CO2, I can use my balanced chemical equation to convert it to moles of calcium carbonate and then grams of calcium carbonate. Okay, so let's do it. I know the volume is equal to 3.45 liters. The temperature, go ahead and convert it to Kelvin, but it's 318 Kelvin. And I know the pressure is 1.37 atmosphere. Okay, so now I can use PV equals nRT to find N. That's my number of moles of carbon dioxide. So I can isolate N by dividing by RT both sides, PV over RT. That's my N. So if I substitute all of these values, 1.37 times my volume is 3.45. Use your units, but I just don't have room here, so I'm not using them. 0.08206, and the temperature, which we calculated, 318 Kelvin. That gives me an amount of moles of 0.181 mole of CO2. Okay, now I have moles of CO2. I can relate the moles of CO2 by using the chemical reaction to moles of calcium carbonate. It's a 1-to-1 ratio, which means that I'll work it out for you, but if it's a 1-to-1 ratio, this should be the same amount of moles of calcium carbonate. So I have moles of CO2 times, I know for every 1 mole of CO2 that reacts, I get 1 mole of calcium carbonate. So my moles cancel, leaving me with moles of calcium carbonate, which is 0.181 moles of calcium carbonate. 3. Okay, now that I have moles of calcium carbonate, I can convert that to grams by using the molar mass. I'm not going to show you how to do that. You should know how to do it by now. So I take the amount that you're given. Do not use the molar mass first. So 0.181 moles of calcium carbonate. And you multiply that by, so I know 1 mole of calcium carbonate weighs 100.09 grams. My moles will cancel out, and you should get 18.13 grams of calcium carbonate. Okay, so this is one of those problems where we combine the gas laws with a stoichiometry problem and you can only do this obviously if you have a gas in the reaction. If this wasn't here, then we obviously couldn't use the PV equals nRT because that's only for gases. But you can do this when you have a gas as part of a chemical reaction. You can figure out the number of moles of that gas by using PV equals nRT, and then you can do stoichiometry with that amount of moles. Okay, so let's look at the last problem that we're going to do in lecture. I am going to work a bunch of other problems and post those separately, but these were just the ones that I cover in lecture. Okay, so let's read the last problem. A sample of hydrogen gas has a volume of 8 liters at a pressure of 5 atmosphere and a temperature of 25 degrees Celsius. What volume of gaseous water is produced in the following reaction at 150 degrees Celsius and 0.947 atmosphere if all the hydrogen reacts with copper 2 oxide? So here's my reaction. Copper 2 oxide. I know the 2 tells me copper is a 2 plus. I know oxygen is a 2 minus, so this is a neutral compound. Copper 2 oxide plus my hydrogen gas, H2, gives me copper solid plus H2O gas. Okay. I'm going to erase this here. What do I have? I am given an initial volume for hydrogen. So it says a sample has a volume of 8 liters and a pressure, P1, of 5 atmosphere and a temperature, T1, of 25 degrees, which would be converted to Kelvin, would be 298 Kelvin. What volume of water is produced, once again, it's a gas, if all the hydrogen gas reacts with copper 2 oxide, but in the following conditions, at 150 degrees, so my T2 is 150 degrees Celsius, which is equal to 423 Kelvin. At pressure of P2, 0.947 atmosphere. Okay, what will be the new volume, V2? Now, the volume of water, remember, is going to be the same as the volume of hydrogen because they're in the same container. Okay? So, first of all, let's look at this reaction and let's figure out if everything is balanced. I have 1 copper, 1 oxygen, 1 oxygen, 2 hydrogens, 2 hydrogens. And because I have a 1-to-1 ratio here, that is why the volumes are going to be the same. Okay, so what do I have? I have V1, P1, T1, P2, and T2. I'm missing V2. Okay, I can do that very easily. I can solve for V2 by using the ideal or the combined gas law. Okay, what does the combined gas law say? V1 P1 over T1 is equal to V2 P2 over T2. To isolate V2 is equal to V1 times P1 times T2 over T1 times P2. Okay? Now, I can plug in all the values that I know. So 8 liters, it's my V1, multiplied by P1, which is 5 atmosphere. Make sure you don't mix these up because you'll get the wrong answer otherwise. T2 is 423 Kelvin over T1, which is 298 Kelvin, multiplied by pressure, P2, which is 0.947, 0.947 atmosphere. Okay, my Kelvin cancels, my atmosphere cancels, leaving me in liters, which is 59.96 liters of hydrogen. Okay? Now, I can I can say that because hydrogen and water vapor have the same amount of moles, so 1 mole of hydrogen gives me 1 mole of water. That means that because they're in a 1-to-1 ratio, the same amount of moles of hydrogen there are, you will have the same amount of moles of water vapor. And remember, if you have the same conditions for these gases under the same amount of moles, they will have the same volume. And under the same conditions, having the same number of moles, they will have the same volume. So this is also the volume of water vapor, 59.96 liters of H2O. If they didn't, if they had a different ratio, I would first take this volume, convert it to moles of hydrogen by using PV equals nRT, and then take moles of hydrogen, use the balanced chemical equation to convert it to moles of water. Let's say it was a 1-to-2 ratio. Then I would double the number of moles, then take that, plug it back to PV equals nRT to find the volume for the water vapor. But in this case, because they have the same ratio, molar ratio, it's a 1-to-1 molar ratio, they will also have the same volume. You can convince yourself, so go ahead and do this. Calculate from this volume and P2 and T2, calculate the number of moles of hydrogen gas using PV equals nRT, right? So PV equals nRT, solve for N, you know R, T, use T2, P, use P2, V, use this 59.96, so find N. That is going to be the same number of moles, because it's a 1-to-1 ratio, same number of moles for hydrogen, or for water vapor. Then take that number and put it over here, use PV equals nRT once again, and calculate the new volume. You'll have the number of moles of water because you'll relate that from the stoichiometric relationship here. You'll use T2, you'll use P2, you will solve for volume, and you will find but they'll have the exact volume because they have everything else is the same. The pressure is the same, the temperature is the same, the number of moles of both are the same because they have 1-to-1 ratio. Go ahead and do that, and when we have the synchronized video session, the big blue button sessions, if you're struggling with it, you can always ask me questions, and I will be more than happy to help you solve it. Okay, this concludes our chapter 8.